Hi there. My name is Miss Townsend and I love math. Welcome to Math with Townsend. This video is for grade 9 academic students who are studying the measurement and geometry unit. This is part 3 of that unit where we look at optimization, and it's actually video number 4 of optimization. In the previous videos, we defined optimization and what it means in a math setting, and we explored optimization. In particular, we looked at how to optimize two-dimensional rectangles. But we did talk a little bit about three-dimensional optimization as well, so let's summarize what we've seen in the other videos. Well, we've seen that when you optimize in two-dimensional space, the key is right here, make your side lengths equal. If you can make the side lengths of a shape equal, then you're probably working on optimizing that shape. So for example, in a rectangle, it's optimized when the side lengths are the same, and that actually means you're making a square. A square is an optimized rectangle. In a parallelogram, it's optimized when all sides are the same length. And when that happens, you have what's called a rhombus. So a rhombus is an optimized parallelogram. A triangle is optimized when all sides are the same length, and that's a special triangle called equilateral. And again, an equilateral triangle is an optimized triangle. We don't worry about optimizing trapezoids, not in grade 9, and circles are automatically optimized. So we only have to worry in 2 dimensions about optimizing rectangles, parallelograms, or triangles. And all of them are optimized when the same thing is true, when all the sides are the same length. In 3 dimensions, we learned that optimizing a rectangular prism occurs when the length, width, and height are all identical. Again, when all dimensions are the same, you have an optimized shape, and in this case, that's a cube. So a cube is an optimized rectangular prism. A cylinder is optimized when the diameter equals the height. So again, when the dimensions match, just be careful that you're thinking diameter here and not radius, because in this diagram, it sure looks like the dimension of interest is radius, but it's actually the diameter that you want to match the height. And when you match the diameter to the height of a cylinder, then you've optimized your cylinder. We don't have to optimize a sphere, it's already done for us. And in grade 9, we're not going to worry about optimizing cones, square-based pyramids, or triangular prisms, because the math behind that is a little harder than we need to deal with. But you'll have fun in calculus when you look at optimization really intently. So we'd started to look at some questions related to three-dimensional optimization. We had this question: how would you arrange 200 interlocking cubes into a square-based prism so that it had the smallest surface area? So we noticed that the word smallest is a key word for optimize. If we're trying to make something the smallest we can, then we're trying to optimize something. And we know that if we're optimizing a bunch of rectangular shapes, the answer is to make a cube. Now we discussed that if you actually had interlocking shapes, so interlocking shapes are a little trickier to work with because you might not be able to make a perfect cube out of them, right? You might not be able to make exactly a cube, but if you actually had these shapes in front of you, you would certainly build towards that idea and make it as cube-like as you could. So then we talked about, well, what if instead of 200 interlocking cubes, what if we just said that we have to create a volume of 200? So we have to make a box, a rectangular prism, and we must have a volume of 200, let's say, centimeters cubed. And we're trying to optimize surface area. So we know that we need to create a cube. We know that. That's the rule for optimization. And a cube has length, width, and height that are identical. So the volume of the cube would be x times x times x, or x cubed. So then we said, well, what value must x take if the volume is 200? And here we ran into a bit of trouble. This is why that last video we were only able to do one math question, because x cubed equals 200. So what does x equal is not a question that you've answered yet in your math career. You certainly know how to deal with x squared equals something, because you know that to get rid of squared, you do something called square root. Well, there is also something called cubed root. And this is what cubed root looks like. And I talked a little bit about how to find and use that button on your calculator. And you should have discovered that by pressing the buttons in the right order, the cubed root of 200 is 5.84. And therefore, if I want a cube with a volume of 200 and an optimized surface area, then I need length, width, and height to all be 5.84 centimeters. And that's what we had finished doing in the last video. So let's look at another question. It says, and pretend you don't see this, we'll talk about this in a second. Loki has 2.5 square meters of sheet metal to build a storage box for wood. If the box also includes a lid, what are the dimensions of the box Loki could make that has a maximum volume? Well, the keywords here are maximum. That means that we're obviously trying to make something optimized, and we're optimizing a box. So you already know that we want to make a cube. So an optimized box is a cube. Now in this question, we're maximizing volume, and that must mean that this is the surface area. So the surface area is 2.5 meters squared. Because when you make a box out of sheet metal, you don't fill in the box with sheet metal, you just create the outside surfaces. So the surface area is 2.5 meters squared, and the question is, what are the dimensions? What is the length, width, and height that will give me a maximum volume? Well, we know it's a cube, so we know that we have x, x, and x. So what would the surface area be? Well, let's think about this logically. If it's a cube, then each one of the 6 edges or 6 sides of the cubes must have the same amount of material. So to start with, I'm going to take the 2.5 meters squared that I have, and I'm going to divide it into 6 pieces. And that'll tell me how much material I have for each side. So for each side, I have, excuse me, about 0.42, oops, I have about 0.42 of a square meter. So each side is going to be a perfect square with an area of 0.42 square meters. And again, each side has dimensions x times x. Therefore, I can say that x squared equals 0.42. So I'm going to take the square root. And the square root of 0.42 is 0.65 meters. Or you could say 65 centimeters. So if I make a cube where each edge is 65 centimeters long, then I will have a volume that is maximized, and I will have used exactly 2.5 meters squared of sheet metal. And you can check that, of course, by doing the math, because 65, each of these sides is 65 times 65, and then there's 6 sides. Now, that's one method of doing it, and you'll see I didn't use my formula sheet, I simply used logic. If you wanted to use your formula sheet, you certainly could. So let's look at that method just quickly for a second here. And if you look on your formula sheet, you will see that the formula for the surface area of a rectangular prism looks like this. So this is for a rectangular prism, but we have a special rectangular prism called a cube. And so instead of width and height, we have x times x. Instead of length times width, we have x times x. And instead of length times height, we have x times x. So in fact, the surface area, ooh, that was weird. The surface area of a cube is 2 times 3x squared, or 6x squared. So if I set 2.5 meters as the surface area equal to 6x squared and solve for x, you'll see that Solving for x is exactly the same method I used, but I didn't use a formula sheet. I just did logic, but it's nice that you have a formula sheet in case the logic didn't make sense. Okay, so let's go on and look at another question. It says 72 meters squared of material is to be made into a cylinder with closed ends. What are the dimensions of the cylinder with maximum volume that could be made? So again, maximum volume. So I must know surface area. Surface area is 72 square meters. Now, if I'm maximizing, I'm optimizing. And an optimized cylinder has a diameter that matches the height. So I'm going to call the diameter x, and I'm going to call the height x. So this is the surface area. And let's go to the formula sheet and look at what the formula is for the surface area of a cylinder. Oops. So surface area of a cylinder is right here, 2 pi r squared plus 2 pi rh. So surface area equals 2 pi r squared plus 2 pi rh. So we need to figure out what x must be to maximize the volume. So what do we know? Do we know the radius? Well, we know that the radius must be half of x, and the height is x. So those are the values we're going to sub in. So 2 pi radius squared plus 2 pi radius times height. So let's do as much math as we can. So 72 equals 6.28 times x squared divided by 4 plus 6.28 times x squared divided by 2. So let's keep going. 72 equals, what's 6.28 divided by 4? So 6.28 divided by 4, so that's 1.57 x squared. And then over here, I'm going to do 6.28 divided by 2. So 6.28 divided by 2 is 3.14 x squared. Collect like terms. 1.7 plus 3.14 is 4.71. And then so again, my goal is to solve for x, so I'm going to divide both sides by 4.71. And that gives me 1.53 equals x squared. And so finally I can solve for x. Yay! The square root of 1.53 is 1.24. So that means the optimized cylinder that has a surface area of 7.2 meters squared has a diameter of 1.24, 1.24, and a height of 1.24. So diameter equals 1.24, and height equals 1.24. And I think this question was in meters. So again, what did we do? We knew that we had to have the diameter and the height exactly the same. So we gave them the name x. And that meant that the radius was x over 2. We subbed the values for radius and height into our surface area formula, and we also subbed the surface area in. And then we just had an equation to solve for x. And we ended up doing really good algebra and getting that x was 1.24, meaning the diameter and the height would both be 1.24 if I wanted to maximize that cylinder. Now there are a lot more questions we could do on optimization, but obviously it's not a huge and major part of the course because otherwise we would have spent a lot more class time on it. However, it is an important subject, and by all means, if you want to see more work or more questions, please post in the comment section. Otherwise, we're done the measurement unit, and the only thing we still have to discuss in these videos is geometry. So I'll meet you at some point in a geometry video. Happy studying!